Dear students, in this video we are going to prove the converse part of previous theorem. Okay, in previous theorem we have already seen if the matrix space is connected, then every continuous function from x to plus minus 1 is constant. But now we have to prove if every continuous function from x to plus minus 1 is constant, then x must be connected. Getting? So this thing we have to prove. So let me write the given thing. So given thing is we have every continuous function. Okay, we are not talking about any special function. We are talking about every continuous function which is defined from x to plus minus 1 is constant. That means if you find any continuous function, okay, if you define your own continuous function from x to plus minus 1, then it must and it is constant, then you can say x is connected. So to prove that x is connected, okay, so I'm going to follow the same method which I have already told you in our previous video. That method is when we have to prove anything, assume exactly opposite to that. We have to prove x is connected, I will assume x is disconnected, and then I will write some logical statements. At the end we will get a big contradiction, then we will rectify our statement, and then we will get the required result, right? So let if possible x is disconnected. I am assuming that x is disconnected. Okay, so let me show in the picture. Suppose such matrix space we have which is x, okay, and we are saying x is disconnected. Okay, disconnected, that means this kind of thing we will have. Get it? Disconnected. So if x is disconnected, the various definitions of disconnected matrix space we have already seen in our previous videos. So one of the definitions I'm going to use here, x is disconnected, therefore there exist a and b subsets of x such that, okay, if x is disconnected, we can find two subsets of x such that the first thing, their union is x. As you can see in this diagram, you can say this is a and this is b. Second thing, a and b are non-empty, right? There are some elements in a and there are some elements in b. Third, a intersection b is equal to phi. Both sets are disjoint. There is nothing common between a and b. And four things, a and b are open, right? A and b are open. That means various definitions are there of disconnected matrix space. If you say a and b are closed, that is also one of the definition, but I am using this one here, a and b are open. So we assume x is disconnected. So this kind of thing we have, right? See, the given thing is every continuous function from x to plus minus 1 is constant. That means in a given fact, they are talking about a continuous function. That means here also we must have some function. We must have some function, then only we can use the given thing. They have not given any function here, so it's our duty to define any function. Okay, so let us see how to define the function. We are interested in any function which is from x to plus minus 1. Okay, what we want a function from where to where, x to plus minus 1, x to plus minus 1. So we want one function, so I'm going to define a function. I will consider all points of a are mapping to 1 and all points of b are mapping to minus 1. We were interested in function, so I'm defining in this way. So see, now we define, I'm going to define a function from where to where, x to plus minus 1 as, see how I define, f of x is equal to 1 if x belongs to a. If you have any point of a, it will go to 1, and if you have any point of b, it will go to minus 1. Okay, so now right now I have a function. Okay, So now my target is to check whether it is satisfying this condition or not. Okay, what we want a continuous function. My target is to prove that this is continuous function, right? Continuous function. And see how to prove the function is continuous. Various definitions are there. You have epsilon delta definition to prove the function is continuous, but I think that is not suitable here to use epsilon delta definition. See, there is one more result, that if you have any open set in codomain and its inverse image is open in domain, then you can say the function is continuous. And this is true for every open set in codomain, right? If you have any open set in codomain, its inverse image must be open in domain, right? If this is true, then also you can say the function is continuous, right? This thing I'm going to use. See, this is very standard result and we have already covered, and its proof is also already covered in the playlist of continuous functions. If you are interested, you can go and watch that playlist also, right? Let us move further. So as you can see, this is a finite set. How many elements are there? Just two elements are there, 1 and -1. If you have any finite set, every set is open. Getting in a finite set, every set is open. So see here, plus -1 is a finite metric space. Okay, so what will be the subsets of plus and -1? Empty set phi, this is subset of this plus and -1. Singleton 1, that is also subset of plus -1. Singleton -1, that is also subset, and 1 and -1, right? 1 and -1 are open sets in this finite metric space plus 1 -1. Since the reason is because every subset of finite metric space is open. Okay, this part also we have already covered. This part is also already covered. So right now we want some more space to write. Just make a screenshot of it, then we will move further. So let us find inverse image of all these subsets, right? Inverse image of phi, f inverse of phi. Okay, inverse image of empty set is obviously empty. Inverse image of 1, right? So inverse image of +1 will be A. Inverse image of -1. The inverse image of -1 is B. And inverse image of +-1, right? So inverse image of this +-1 will be the entire matrix space X, right? So in this way, we got the inverse image of all open subsets of a codomain, right? But see, phi is always open. A is open, right? A is open. Here we had written few minutes before. You can go back and check. So A is also open, B is also open. We have already declared A and B are open. And X is the entire matrix space. So that's why obviously it is open. So here, phi, A, B and X are open in X. Getting every sets, all these sets are open in X. That means what I want to say, if you take any open set in codomain, its inverse image is open in domain, right? So therefore, F is continuous. Okay, F is continuous. I should mention the reason. G is open in Y implies F inverse G is open in X. If you have this kind of thing, then you can declare F from X to Y is continuous. This is one standard result we have already covered in playlist of continuous functions, right? If you have any open set in codomain, its inverse image is open in domain, then you can declare the function is continuous. So the same thing I am using to prove that this F is continuous. So right now we have a function. Okay, right now we have a function, as you can see this diagram, F from X to +-1. We have a function from X to +-1 which is continuous, but it is not constant. Why we are saying it is not constant? Because some points of X are going to 1 and some point of X are going to -1. That's why it is not constant. So which is contradicts to the given thing what we have already declared. Every continuous function from X to +-1 is constant. and we get a big contradiction here, right? So why we are getting a contradiction? Because of our wrong assumption. Our assumption was x is disconnected. That is wrong. Therefore, we can say x is connected. Okay, so I'm going to write all these things here. Okay, just let me remove this part. So I have written everything properly here, right? F inverse of 1, which is A, it is non-empty. F inverse of minus 1, which is B, that is also non-empty. So we get a continuous function which is not constant, which is from x to plus minus 1. And we get a contradiction to our basic given information. So we get a contradiction because of our wrong assumption. Our assumption was x is disconnected. That is wrong. That means x must be connected. Okay, so in this way we have proved this theorem. See, next video we are going to combine both these theorems, right? So if you simply combine the proofs of these two videos, you will get the proof of that theorem also, right? But that theorem is so much important from exam point of view also, as well as to prove some other theorems, some results, and solve some examples also. It is quite important, right? So we will meet in next video and we will discuss that theorem. Thank you.